Welcome to The Explainer. Today, we are completely reframing the narrative around one of the absolute most fascinating and, frankly, misunderstood objects in our universe. I'm talking about the brown dwarf. For the longest time, the cosmos seemed so neatly divided, right? You had your stars over here, your planets over there. But brown dwarfs, they completely blur those lines. They literally force us to rethink planetary systems altogether. So let's just jump right in and dig into what they might be hiding out there in the dark.
Okay, let's take a quick look at our roadmap for today. We'll hit the stars that failed, the fusion boundary, born like stars or planets, exotic weather and spectral types, magnetic fields and powerful auroras, and finally, the search for exomoons.
Part 1. The Stars That Failed, Unpacking an Unfair Cosmic Label.
So, what exactly is a failed star? Well, when astronomers first theorized these objects back in the 1960s, they realized there literally had to be a bridge between the heaviest gas giants and the absolute lightest stars. It sparked this massive question. What happens when a collapsing cloud of interstellar gas just, doesn't quite make it to full stardom? And honestly, we didn't actually find an unambiguous one of these until 1995.
The really crucial point here is that a brown dwarf is a literal intermediate object. It's the ultimate middle child. It possesses some distinctly planet-like characteristics, think complex atmospheres with thick clouds, while still retaining very star-like attributes, like forming in total isolation from a collapsing cloud of gas and dust. They just simply aren't massive enough to generate the extreme core temperatures and pressures you need to sustain the proton-proton chain. That stable fusion of ordinary hydrogen into helium that powers true stars like our sun.
The contrast is absolutely wild when you lay it out. Think about it. A main sequence star sustained stable hydrogen fusion for billions of years to support itself against gravity. A gas giant planet, on the other hand, has zero fusion going on and forms in an accretion disk. But the brown dwarf, it's trapped right smack in the middle, exhibiting this bizarre continuum of traits from both sides of the spectrum.
Moving right along to Section 2, the fusion boundary, a matter of mass and ignition.
Now in space, mass is essentially destiny, right? And 13 to 80 represents the critical Jupiter mass range of a brown dwarf. Astronomers generally agree that anything below 13 Jupiter masses is a planet, completely incapable of any thermonuclear reactions. Meanwhile, anything above roughly 75 to 80 Jupiter masses has enough sheer gravitational weight to crush its core and ignite stable, ordinary hydrogen fusion. That officially makes it a main sequence star.
It's super interesting how these exact thresholds break down. Even though brown dwarfs can't fuse regular hydrogen, their mass, again sitting in that 13 to 75 Jupiter mass sweet spot, generates just enough core heat to temporarily fuse a heavy, super rare isotope called deuterium. But because deuterium is so incredibly scarce out there, the fuel runs dry pretty quickly, usually in just 3 to 30 million years. And after that, the brown dwarf just begins to slowly cool off. Section 3. Born like stars or planets, solving the taxonomic mystery. Okay, so knowing their mass limits and their super fleeting period of fusion, we have to ask, how do these massive glowing orbs actually form in the deep dark of space? Are they just tiny stars, or are they overgrown planets? Well, the fine detail is actually still fiercely debated. Brown dwarfs seem to have these hybrid origins, some likely formed through the gravitational collapse of gas clouds, exactly the way stars do. But get this, we also see planetary mass objects orbiting brown dwarfs, and some researchers argue that brown dwarfs themselves could actually form through planetary processes. We're talking core accretion, or even the gravitational fragmentation of a circumstellar disk, which is known as disk instability. I love this quote from the source material because it just perfectly captures the beautiful chaos of their origins. Inside the brown dwarf desert, stellar and planetary processes met and produced almost indistinguishable objects. Researchers looking at this so-called brown dwarf desert, which is a region close to host stars where brown dwarfs are mysteriously super rare, found that the boundary between star formation and planet formation just completely breaks down here. It really suggests that brown dwarfs exist on a sliding scale in nature, rather than fitting neatly into some rigid binary box of star or planet. That brings us to Section 4. Exotic weather and spectral types, from blazing heat to planetary clouds. If we trace their thermodynamic trajectory, they start out incredibly hot, glowing this deep, intense red at well over 2000 Kelvin.
But with their internal furnace completely empty after about 10 million years, they spend literally billions of years just steadily cooling down and growing fainter. Which, by the way, is exactly why we usually have to hunt for their faint heat signatures using specialized infrared telescopes. Astronomers actually categorize this whole cooling sequence into spectral classes. They start as L dwarfs, cool into T dwarfs, and eventually become Y dwarfs, which reach freezing, straight-up planet-like temperatures.
Because of this extreme, relentless cooling, older brown dwarfs develop some unbelievably dynamic atmospheres. We're talking exotic weather phenomena that easily rival the gas giants right here in our own solar system. Picture giant, complex cloud layers made of various chemical species, including actual water and methane, just swirling around under crushing surface gravity. The result? Massive, violent Jupiter-like storms.
Section 5. Magnetic Fields and Powerful Auroras. The Shocking Radio Reveal. So what? Are brown dwarfs just cold, dead objects slowly fading away into the dark? Not at all. In the early 2000s, scientists were completely baffled when they detected pulsing radio waves coming from these dim objects. At first, they figured, okay, it must be a hot corona driven by magnetic flares just like our sun. But there was a massive problem with that theory. Brown dwarfs simply do not generate large solar flares or charged particle emissions like main-sequence stars do. So where in the world were the radio pulses actually coming from?
To crack this mystery, we actually have to look closer to home. Here on Earth, the solar wind from our sun drives charged particles into our magnetosphere, and that creates the spectacular northern lights. But as we just said, brown dwarfs lack a stellar wind entirely. So that means something else, something absolutely incredibly powerful, is generating massive electrical currents within their magnetic fields.
Well, researchers discovered that these pulsing radio emissions, along with periodic hydrogen emissions, are actually being caused by spectacular auroras right near the magnetic poles. Electrons spiral down the magnetic field lines, smash into the atmosphere, and excite the gas. The result is a fantastic light show that is hundreds of thousands of times more powerful than any aurora in our solar system. And the wildest part? Astronomers strongly suspect this massive current might actually be generated by an undetected orbiting planet just plowing right through the brown dwarf's magnetic field.
And that brings us to Section 6, the search for exomoons, looking for life in the dark. That realization, that brown dwarfs could host their own orbiting bodies, brings us to the most tantalizing possibility of all. Now 250. That number is the frigid temperature in Kelvin of WISE 855. It's the absolute coldest known brown dwarf, specifically an ultra-cold Y dwarf sitting just 2.3 parsecs away from Earth. Because it's so close to us, and because its temperature is so surprisingly similar to our own gas giants, it has become the perfect target for the James Webb Space Telescope to hunt for transiting exomoons.
By carefully analyzing 11 straight hours of time series spectra from JWST, astronomers have been actively searching for the tiny shadows of transiting exomoons. The real trick is using different wavelength light curves to disentangle the brown dwarf's chaotic, swirling cloud weather from a true gray exomoon transit dip. Now, while they didn't spot one in this specific dataset, the data proves something huge. We have the technology right now to detect objects the size of Jupiter's Galilean moons or Saturn's moon Titan. In fact, calculations show there's a 91% probability of detecting a Titan-mass exomoon after just 18 of these observations.
So as we completely reconsider what it really means to be a star or a planet, we are left with a pretty staggering thought. If we know that moons like Europa and Enceladus, right here in our own solar system, harbor deep subsurface oceans, we really have to wonder. Could the moons orbiting these misunderstood free-floating brown dwarfs out in the pitch black of space actually be the next great frontier in our search for habitable worlds? Keep your eyes on the data, folks, because the universe is about to get a whole lot bigger.